last thing on your notes is a couple notes starting complex numbers, right? So we're just gonna take it from the top, and then I'll consult my notes in a minute. So we're doing complex numbers. And we'll just begin with the motivation. You've got the quadratic formula. And you have its solution. X equals 1 over 2a negative b plus minus square root of b squared minus 4ac. Famous expression here. And of course, you have to analyze this thing to see if it's even legit, because it's not supposed to be negative. But if you just define a negative square root of a -1, then suddenly you don't have to do anything fancy with this. So you extend the concept of numbers to include the square root of -1. Or x squared plus 1 equals 0, right? That would be the simplest version of this problem here. And then let I equal the square root of -1 such that I squared equals -1. And it turns out you can just define a set of complex numbers this way, and you get consistent algebraic qualities. Just as regular algebra that we had before holds true as well here. So let's see here, this is going to be the set of z equals x plus iy, such that x and y are real numbers, and I squared equals -1. So then we have to work our way through the algebraic properties. Okay? We have to work our way through the algebra, and then to make sure everything works properly, we have to have addition. Right? And so addition, z1 plus z2 equals x1 plus iy1 plus x2 plus iy2. And yeah, you define the addition that you add the two real parts and then two so-called imaginary parts. And if you do that, addition and subtraction are well defined, and you have that, okay? So that's addition and subtraction. Now multiplication is less fun. So you have addition, we have multiplication. Addition is, like I said, subtraction. Well, multiplication, we have to multiply z1 and z2. So you have x1 plus iy1, x2 plus iy2. And yeah, there's nothing to be done but multiply these things out. What we're going to find, though, we have x1, x2. And then when we multiply these second ones out, we have y1, y2. I times I is -1, so we have minus y1, y2. And then the imaginary parts will have I times y1, x2 plus y2, x1. Good, so that's all well defined. It's already looking a little less fun than before, okay? Now division is where it really gets interesting. So we're going to divide two complex numbers. So far I'm just following the rules. So here goes. What about division? Division, multiplication, division. So now we have stumped. We're going to have to introduce another idea here. So I'm just going to write equals question mark. What we do now is define the complex conjugate as follows. So if z is equal to z, I'm sorry, if z is equal to x plus iy, then z complex conjugate star is x minus I times y. And you'll also see z star z bar on top. Okay. So we'll use the star. Now what happens here is that z times z star is equal to x plus iy, x minus iy. And what's going to happen is the cross, we're going to multiply the whole thing out just for once. We'll have x squared, I times minus I is plus 1. Okay. So we have x squared plus y squared plus ixy minus ixy. So these go away against each other, and z star is just x squared plus y squared. Always positive unless z is equal to 0. So yeah, now we can make this division move. Subtraction, multiplication, division. So now let's do the division again. We have x1 plus iy1 divided by 2 plus iy2. And we're going to multiply by 1, namely numerator, denominator by the denominator complex conjugate. x2 minus iy2. So now I've multiplied by 1, and the denominator is just well behaved because it's just x2 squared plus y2 squared. So that's how we get around that. And now I have to multiply these out. And what are we going to have? We're going to have x1, x2 plus y1, y2. And plus I times y1, x2 minus y2, x1. Okay. So now we have well-defined addition, subtraction, multiplication, division. But everybody's got to admit that this doesn't look like a lot of fun. Okay? But it doesn't matter because we have all these operations in principle, and we can do all algebraic principles. There's one thing about the complex numbers, and namely, let's go ahead and write the magnitude of a complex number. And the magnitude of a complex number is equal to the square root of the number times its complex conjugate, which, as we just saw, was x squared plus y squared. If we take it, oops, that's what the equal sign, x squared plus y squared. So the complex numbers are not an ordered set. We got some. Not an ordered set. So unlike the real numbers where you have greater than, less than, we don't have that with the complex numbers. Because there's a whole lot of complex numbers with the same magnitude. Okay? A whole circle's worth, so to speak. So yeah, so the complex numbers are not ordered in terms of magnitude, but magnitude is sufficiently well defined that you can do all manner of limits. Everything you have to do in calculus, you can do with the complex numbers. Okay, let me go ahead and complex number. We have all the arithmetic properties. So the next thing to do, and this is already implicitly right here, is introduce the complex plane. So addition, subtraction, multiplication, division, that's fine. So because we have a two-component number, two field components, so to speak, we can visualize them in the complex plane. And this is really the key. So now what we do, we have a real axis and an imaginary axis, and any complex number here, z, can be written x plus iy. And one thing you immediately have off of this is that the complex numbers with respect to addition are vector space. We're talking about vector spaces, and we'll immediately get that. In fact, you can see these complex numbers just add like vectors, add like arrows. If you take one, it will do different colors. If you had so suppose you have x1, y1. You treat this like an arrow, and then you're going to add an x2 and a y2 like that. Yeah, then the resultant is in fact going to be x1 plus x2 plus y1 plus y2. Just going to add like vectors. And subtraction is the same way. So you have a sum or a difference vector. Exactly, you can visualize exactly the way you do vectors in the plane. So that's we'll see that it's an added benefit here. But when we're in the complex plane, we have another thing that we can do, another picture here. So we have our complex number. Here's that x, y. Okay. We can represent it now. Magnitude and an angle with respect to the positive axis. And I've got this z here equals x plus iy. Here's another place to introduce some stuff. I have z is generally its real part of z plus I times its imaginary part. So that's another way to look at it. And if I take these features, namely that angle, I can say I have z magnitude times cosine of theta plus I times z magnitude sine of theta. And if I want, I can name this R, with the understanding that that's what it is. Okay. So I can write things simply as well. So there it looks like we're just in the plane with plane polar coordinates. So what about the complex numbers with magnitude 1? The unit circle, right? That would be this, and that was with that x squared plus y squared already. So the set of complex numbers of magnitude 1, that defines a unit circle in the complex plane. A couple other things before we get to that. Yeah, let's go ahead and mention this as well before we get to the unit circle. So I have these definitions, real and imaginary part, so forth. So one thing we get is off of what I just wrote there. Z, so I'm going to write this. Z equals X plus IY. Z star equals X minus IY. So if I add Z plus Z star, I get 2x. If I divide that by 2, I get the real part of z. So this is the general formula for finding the real part of a complex number. You have the number, its complex conjugate divided by 2. And what if I subtract one from the other? If I do z minus z star, okay, now I've got 2y there. So if I divide that by 2 times I get the imaginary part of z. So that's a way to isolate the real or the imaginary part, just on general principles. Okay, so yeah, those are just things we learn and use a lot, but here comes the most important point. So we have the unit circle of complex numbers. So set of z element c such that z magnitude equals 1, of course, into our unit circle. So now I've got a 1 here, and I've got a theta. And I have this formula right here. So we're on the unit circle, it's just going right. We've got z equals times equals cos theta plus I sine of theta. So the next thing is named after Euler. I'm assuming he discovered it. Is there anything that Euler didn't discover? I don't recall. But yeah, what we're going to do is e to the z. We've been studying the Taylor expansions, and we've studied convergence. We would have z to the k factorial, k equals 0 to infinity. Okay. This will be very well defined. The convergence is good. We know we can do absolute values. We can do D'Alembert criterion and so forth. Okay, so there's no problem with this. Instead of the general form, which is well defined for the moment, we're going to do the z equal I theta. Theta is real. Okay. So now z is a purely imaginary number, and we're going to do e to the I theta. We'll go ahead and write this out here. I theta k factorial 0 to infinity, and we'll just go as far as the board lets us. K equals 0, we just have 1. For k equals 1, we have plus I theta. For k equals 2, we get an I squared, which is minus 1, so we get minus 1/2 theta squared. What's I to the third power? Negative I, because it's I squared negative 1 times I, so we end up with negative I theta cubed over 3 factorial, and then I to the fourth, I squared times I squared, negative 1 times negative 1 is positive, so we get plus theta to the fourth over 4 factorial, and now we're starting to see the pattern. Okay, we could do a couple more. So I to the fifth, I to the fourth was negative, we're getting a plus I theta to the fifth over 5 factorial. I'm going to write and plus and so on, because we have a real and an imaginary infinite series. The real one is 1 minus theta squared over 2 plus theta to the fourth over 4 plus minus dot dot dot, so that's alternating. And then we have plus I theta minus theta cubed plus theta to the fourth over 5 factorial, and so on. So this is one of the all-time great moments in math, because this is the cosine and this is the sine. So we have cosine of theta. We have cosine theta plus I sine of theta. So e to the I theta Euler's formula, one of many. Okay. Formula. And it's this that makes the life of the complex numbers so convenient. Okay. If all we had was all of this algebra, we'd never get to love it. But right now we can do all kinds of amazing things with Euler's formula. Addition, subtraction, multiplication, division, roots, powers, etc. They're all dealt with here very easily, where they'd be a little bit nightmarish with just the algebraic properties. Good. Yeah, so let's stop for a moment. How well do you guys know Euler's formula? Anybody seeing it for the first time? Nobody, right? It's nice to see how it's developed, and we've systematically done the Taylor expansions. If you want, you could inspect the convergence of it, but the convergence of this is just like the convergence of the real Taylor expansion, of the real exponential expansion. So we don't even have to worry about that. It's all well defined. So now we can start doing interesting math with this. Let's see what we have. Yeah. Multiplication, division, everything else. We're going to start tackling those and get a couple of good problems out of this. And these things as well, we'll see all these things come into play. So I'll erase all this. Start with Euler's formula. So once again, we'll just have E I of theta cosine of theta plus I sine of theta. Okay, so addition, nothing changes. Multiplication, C1, C2. In fact, let's go ahead and write I'll go ahead and write R e to the I theta. R is equal to the square root of C star is equal to the square root of R e to the I the complex conjugate, you can just replace I with negative I. And that's because we had that table, we had that series expansion, we could just replace I with negative I for all of those signs. So yeah, that's what we do. Let's go ahead and continue with this. So we have r squared e to the I theta minus theta. That's the punchline on this one, right? Theta minus theta is 0, e to the 0 is 1. So that takes care of that, and then the square root of r squared is just r. So that's how that works. Okay. So now we can do z1 times z2. Or how about z1 divided by z2? Remember that one wasn't so great, but now we'll just write r1 e to the I theta 1 divided by r2 e to the I theta 2, and then we just have a quotient of real numbers, e to the I theta 1 minus theta 2. So just a difference of those angles. So the division is now trivial as well. And the multiplication, of course, z1, z2, r1, r2, e to the I, theta 1 plus theta 2. So yeah, the properties of the exponential function allow us just to do everything that we want. Here's an interesting one. I can express I. Actually, let's go ahead and draw a circle. Let's draw this in the complex plane. So we've got our complex plane here. And now our theta. So the multiplication of two numbers, you're just multiplying their magnitudes and adding the arguments of the angle. So you multiply two numbers, you're just adding those arguments. So especially if you're on the unit circle, it's really simple because you're multiplying two numbers and adding the arguments just rotates the thing. Okay? Pointing somewhere else on the unit circle, if you're on the unit circle. Now, what about I? Where does I lie on the unit circle? Right there. Okay. So we can say I is equal to e to the I pi over 2. That's its expression. And so if we do I times any old z, that's e to the I pi over 2 times r e to the I theta. Okay, so that was the z, right? And now we'll have r e to the I theta plus pi over 2. So what's the significance of adding pi over 2 to an object? If I multiply this complex number, then it's actually going to be pointing that way, is it not? If I add 90 degrees, right? So if that's one theta, then theta plus pi over 2 is going to be pointing that direction. So I does something very special. It just rotates it by pi over 2. And as soon as we're doing kinematic type of things using this, and we'll see some significance of that as well. So let me see where I do that. Let me write a couple of homework problems now with all of these. this out, you have to have done this at least once. We'll get the addition theorems for trig functions, cosine and sine addition theorems. So just go ahead and do that. Cos theta 1 plus theta 2 and sine theta 1 plus theta 2 addition theorems. Anybody not done those before? It's a good review if you haven't done in a while. So yeah, you just multiply these out and the addition theorem just fall right into your lap. Okay, very nice. Another thing I'd like you to try is just, so here's your problem. This one's easy. R e to the I theta is equal to 3 plus 4i by r theta. That one you can kind of just do by memory. So what if we just put some arbitrary numbers in there? 6 e to the 2i is equal to a plus ib. Sine A and B. And the thing you have to know about this one is that's 2 radians. Okay, I have to say 2 radians. So over here, 2 is 2 radians. But what's 2 radians? Pi radians is 180 degrees, so 2 radians. You have to locate it in the complex plane, and then, yeah, these are both easy, but they're worth doing, right? They're worth checking out just to see these things. Okay, so once we've gotten used to these, we can do a parametrization. Okay, I think this is a little set. Yeah, I'm not sure what week these show up on, but we can do these problems as well. Okay, now let's look at the following. So suppose we have C equals e to the I omega t, omega and t are real. Yeah, we've used this many times before probably when we're studying oscillations. So what's the visual interpretation of this thing? E to the I omega t. T is time, right? Omega is an angular frequency. What do we visualize when we see this? Anybody forming a picture in their mind as we speak? E to the I omega t. In the complex plane, what is it? Could have just been e to the I theta, and theta would be running, and it would be increasing function of theta. So in either case, but omega t is nice to bring into play. Apparently it's the unit circle still, right? And we've got some point here, but as t increases, this thing is just doing a counterclockwise rotation about the circle. You know, and on the other hand, of course, we know now this is cos omega t plus I sine omega t. And this all goes back to the exponential function series expansion. All those properties can be defined with that. So this thing can be differentiated and integrated without any problem. Question?
So does this make like a waveform?
Depends how you want to interpret it. Okay. Right now, though, it's just you could say this is a uniform counterclockwise circular motion around. Well, actually, depending on the sign of omega, let's let omega be positive. Okay, it's a uniform counterclockwise circular motion in the complex plane around, this unit circle. On the other hand, the real part is the cosine, the imaginary part is the sine. And you guys may remember when you first learned about uniform circular motion, they said, okay, if you take uniform circular motion and project the number or the position onto the x-axis, you got that cosine omega t. You guys remember that in physics at some point? Right, and that's exactly what's going on here. So this has all the properties of uniform circular motion, but more because it's a complex exponential, and we can just multiply and do all kinds of easy, interesting things with it. So we can differentiate. So I'm going to put an important note here. This is uniform circular motion. And all I have to do is put a radius here, and then it's a radius something, but uniform circular motion. Counterclockwise on the unit circle. Okay, so we have that, and now we can differentiate or integrate these expressions because they're just well-behaved numbers. That's why by proving the algebraic properties, we can just inherit all this. Because the calculus, you do algebra and then you incorporate the idea of limits. Okay. So what do we have for d, c, dt? Just according to the rules, it's I omega e to the I omega t. Now this is worth pondering a moment. Well, automatically everything falls into your lap here. Okay, so this is our expression. Z dt I omega e to the I omega t. And we started with this uniform circular motion idea. Say we were right there. So at time t, we happen to be exactly here. Okay. We know we're doing uniform circular motion. What's the significance of I times omega e to the I omega t? If this was a position, without dimensions, okay? Without dimensions, I can say R. If this was a position, then this is a velocity, right? Just kinematically speaking. And the significance of multiplying it by I is to add 90 degrees to it. As you guys may remember, when you had the velocity in uniform circular motion, then the velocity was tangent to the position, which is developing like that, right? So the complex numbers are doing that automatically for you. The very fact that you bring down the I means that your new complex number, so here I'll label this one. If this was e to the I omega t, then this one here is I omega, the I omega t. So that's differentiation and its significance. Okay, if we can do one derivative, we can do a second. Okay. So d squared z dt squared is equal to I omega. We get another I omega e to the I omega t. If you want units, just put an R in front of this thing. Okay. And what do we get now? Minus omega squared e to the I omega t. So that's minus omega squared times the original minus omega squared z. And that second derivative is apparently just multiplied but also reversed the direction of that number. Okay? Just as the centripetal acceleration reverses the direction, right, of the position for uniform circular motion. Okay? You gotta admit, that's great. Right? So the complex numbers, they're so important, and we're going to use them a ton, and you can see we really get accustomed to them, and we just treat these things the way we treat other functions. They're very well behaved. The complex exponential is very, very well behaved. Okay? So it doesn't give you any trouble at all. What about integration? Suppose we want to integrate. I'm going to erase a bit. Now the visual on what integration is doing will actually come later in the semester, but for the moment, we can just formally integrate. So, and right now we have to integrate with respect to a parameter. Later we'll integrate with respect to the entire complex number, but this is an important one as well. So e to the I omega t dt, and say we're integrating with respect to t, 0 to t, just to have a concrete example. Well, it's our favorite function, the exponential function. And so the integral will have 1 over I omega e to the I omega t prime from 0 to t, I omega, and then e to the I omega t minus 1. Okay. Does it bother us that we have an I over in the denominator down there? Not in the least. We just leave it there until we have to do something else with it. One thing we can do, we can multiply top and bottom by I, and that gives us I over negative omega. And kind of a useful form would be to get rid of the minus sign, 1 minus e to the I omega t. We're doing things like that in 105 right now. Okay, those kind of things. So yeah, the same thing, really basic integration. We can just treat this thing as a basic exponential function. Okay, so all very nice. Now I'll just put a note here. Note, later we're going to do integration f of z dz. Okay, and that will be an integration through the complex plane. But right now we just treated this as real integral complex numbers. Okay, that's the idea. And this is so much easier. We could have expanded this to cosine omega t plus I sine omega t and done 2 integrals. Okay. Twice as much chance of making a mistake. Okay, let's see where we stand here now. I have a couple more interesting problems for us. Good, we did multiplication by I, that's very important. Convergence, motion. Ah, yes. So, I have 2 interesting problems here. Good, just erase this here. So yeah, you have to get used to seeing z equals e to the I whatever theta as living on the unit circle, living in the complex plane. So this homework problem is to find of 1. We could also do the n roots of negative 1. How can 1 have n roots? Question mark. That's what you're looking at. So, I'm not being paradoxical, I'm not saying this thing at once. Suppose we have z to the n equals 1 has n solutions. One of them, of course, is 1, okay? But if you imagine you're on the complex plane, okay, here's 1. You need a complex number that when it's multiplied n times with itself, lands on the 1. Because, you know, these complex numbers are doing circular motion, so to speak. So for example, suppose I had I right here. What's I to the 4th power? 1, right? So if we could say z to the 4th equals 1 has 4 roots, and what would the other roots be? One of them, z is just equal to 1. You can check that one off. Okay. The other one apparently is I. What's another one? You guys tell me. There are 4 roots, I just gave you 2, give you 2 more.
-1.
Yep, z equals -1. Negative I, yeah. Is that a lucky guess?
No. It's where it looks.
Yeah, z equals -I. So if you look at it that way, the 4th power is a really nice example. So we actually have these 4 roots. And another way to look at it is, each time I take I, I'm taking this angle and ratcheting it around. So pi over 2, pi, 3 halves pi, 1, it's 4th power. If I take -1, that's pi, 2 pi, 3 pi, 4 pi. Okay. And if I take -I, right, I went 3 halves pi, another 3 halves pi, another 3 halves pi, another 3 halves pi. So you land on the 1 each time. And so the homework assignment is to take z to the n and find an expression as n solutions. All right, here, find phi sub k equals 0 to n minus 1. That'll kind of give you a tip. So you can do it for any number, and with 4 it was clear, it kind of ratchets around, and you do it for other numbers as well. Okay, that's a good one to, you know, to realize that there's more going on here. So powers and roots. So what, by the way, would z to the 1/2 power be? Or here, we'll do another one. Kind of examples in the same vein. One more really nice problem, but this is just another example. What's the square root of I? Pardon? Square root of I. Is it I to the I? Here's what we're gonna write. We're gonna write e to the I pi over 2 to the 1/2 power. So that equals e to the I pi over 4. And if you want to look at this visually, this was I here. The angle here was pi over 2. And if you take the square root of that, you're going to land right here. Right? That's the one that squared doubles. You square this one, gives you I again, just like squaring the other ones. So we have a good visual for motion, as physicists, we study motion enough, we can see these things moving around in the complex plane. That's what they're doing for us. So here's the line. How many homework problems do we have now? Have we drawn the line under this week yet? We probably have, yeah. We probably have. But I'm gonna add one more while I've got your attention. Good, so this next one is also very good practice with a bunch of the concepts we've done. Yeah, before we leave, we'll draw the line under and decide what's what. But I want to do this one more problem on the board. So it builds off of what we just did. So it's enough for me to only give away the whole game. Okay. So this is good. Well, I'm sure this one's for next week. Okay. So we're going to look at n numbers on the unit circle. And we now know what that means. And let's draw this. So maybe draw the circle first. Got our unit circle. We start here. This is the positive axis. So we've got this number. 1, 2. Say over to there. Actually, over to here. Draw like that. So I'm going to define these as follows. These are the numbers. This number, that, and that. So to define them is A sub k, n labels them, equals e to the I k theta over n. K equals 0, 1, 2, n. So k is a natural number, theta is a real number. It's one of those angles. Okay? So what we want is the length of this polygon Ln is the length of the polygon. Now it's the point where I don't want to tell you guys too much, but we'll do this. It's the sum k equals 1 to n a sub k n minus a k minus 1 n. And these here, these are the magnitudes, beaten on the wall. These are the magnitudes of what? Of these differences, because remember if you have two complex numbers, their difference works just like difference of vectors. And so you have to apply the magnitude formalism, which will be the square root of the product of this times complex conjugate. It looks kind of complicated, but what you can do is construct this, prove that limit L sub n goes to infinity equals theta. Theta being the arc length, right? So what we're doing is we're constructing a polygon, and as we make the n go to infinity, smaller and smaller increments, then that just turns into the arc length on the unit circle, theta. So this is a really nice problem. Make sure you write it down cleanly. You got to take a few steps, and then when you do this limit, it'll either be an expansion or a L'Hopital type of move to get the limit, so very clean, and this gives a lot of practice with all this complex number stuff. So I think, once you get there, and you know, you can put it off till next week, right, so all's well, but I think you'll enjoy this one, once we get to it. Because after this, we're going to start with Fourier series, right, this Thursday.
This is a next week's that one?
This is the next week. Oh yeah, let's go back to our list of problems. How long is that list now?
Not counting this one.
Good, so this would be 12, so we had 7 on that original list. What would have been the first one that I put up today?
First one you put up today was, multiplying out EI beta 1 times EI beta 2.
Right, okay. Let's do that, let's add to that last week list, that one and that 6e to the 2i problem, right, you see that one? Just locating, so that's all stuff in the complex plane. And then these for next week, I'll add a couple more on Thursday. Good. Good, that's all we've got for today.